and stuff. Then we saw like what are the material properties we need for metal forming, like ductility should be high and yield strength should be low and all those things. And then we saw like the stress, flow stress, and how it affects the behavior of the material.
Yeah.
And then we saw how temperature affects the metal forming, and we saw three different ranges like cold working, warm working, and hot working,
Yeah.
and the advantages and disadvantages of all three of them.
Yeah. Okay, fine. Any other want to add something but missed by Charles? Anyone? No. Okay. Okay, fine. So I think, Charles, I think he has covered whatever we have discussed. So in the material property, we talked about the ductility, high ductility and low in strength. Then also the effect of temperature. So that is much more important. And another two behavior or the properties also we will talk today. One is strain rate. Maybe I just gave the hints only. One is strain rate and second one is friction. Okay. So we have to also understand. So you know already about the strain, right? So we are talking now strain rate, because whenever we are deforming some metal, so that means the the shape changes will occur or the plastic deformation will occur. So I mentioned the strain rate is the speed or the velocity at which the deformation of an object from its original shape occurs. Okay, so that means at which rate, what kind of velocity or what kind of speed you are giving, to which the deformation will take place. Normally, when we are talking about the strength, normally the change in length by the original length. But here also the change is happen. But you have to think about which speed, because you are not only doing one material or one piece, because this is a continuous process. Okay, whenever we are talking about the deformation. Theoretically, a metal in hot working behaves like a perfectly plastic material with strain hardening exponent n equal to 0. So yesterday also we talked about some the stress and diagram, then how it is the elastic behavior, which zone, then plastic behavior, and then also the the strain hardening part, then also the necking part. Just I have shown the diagram. And the metal should continue to flow at the same flow stress once that stress is reached. So that means whenever, because you have to make it in a perfect deformation or in the similar area, you cannot make it vary. So that what you will do, the flow stress, whenever you will reach the maximum one, or when you are thinking that this is now deforming in our desired requirement, then only you have to continue at that flow stress. However, an additional phenomena occurs during deformation, especially at elevated temperatures, known as the strain rate sensitivity. Okay, because whenever you are talking, yesterday we are talking about how maybe somebody was asking how to remove the stress, or maybe what we are telling about the heat treatment. Of course we have to do the heat treatment, there is no other choice. But depending upon the material behavior, depending on the material, for example, if you talk about stainless steel, so you have to go for higher heating temperature, maybe around I think 500 to 600 around. But you have to again the hold it, because whenever you will remember, or whenever you will understand the heat treatment cycle, in that case you have to go for the certain limit. That means you have to increase your temperature up to certain limit. Then you have to also think about the heating rate. You cannot think about just only I am increasing maybe 10 degrees per minute or 2 degrees C per minute. That also will affect, but that depends upon the material. Then one more thing is you have to hold. For example, if you will hold for 1 hour or maybe 2 hour or maybe 5 hours, that also depends based on the material. Then one more thing, you have the cooling rate. That also, where actually you are cooling, whether this is furnace cooling, whether this is oil bath quenching, or maybe oil bath cooling, or maybe this is water cooling. That also will be important, and also at which cooling rate also you are considering there, right? And the strain rate sensitivity of flow stress is an important parameter for deformation mechanism of the materials. So whenever we are going towards the mechanism or the mechanics, what I told, maybe we'll study step by step, maybe a few derivations are there. And then also based on this, maybe we will make some numerical. And the SRS is based on incremental change in strain rate. Incremental change in strain rate during the test performed at a fixed temperature and fixed microstructure. So I think yesterday or maybe day before yesterday, I was talking about when we are applying, I gave the example of maybe copper sulfate. You have to fix somewhere, maybe current if you are fixing, or maybe voltage you are fixing. So similarly here, you have to fix at a temperature and also the fixed microstructure. But because you are thinking also this is my aim or this is my goal, so that means all the the optimal parameters you have to fix somewhere to determine the corresponding changes in flow stress. Okay, so that means whenever you are thinking about my aim is like, the changes in flow stress I am just making, then based on this or with respect to that, you have to fix the temperature. Let's say you are taking 200 or maybe 500 or maybe 1000, whatever you are taking, you have to fix somewhere. And also the mechanical or the morphology or the microstructure of the sample also, that also you have to consider. Okay, so I put one diagram here actually. So this is the stress strain diagram. So just only like, sometimes when we are making, we do not know where this is like, what is the low strain rate or maybe high strain rate, how you have to find. So just I put a schematic diagram here. So if you will see like, the deformation. So I mentioned here the high strain rate deformation, especially shock loading. Okay, where the rate sensitivity can lead to high stress. So that means immediately you have to go for the loading. Shock, like immediately, suddenly. Okay, so you will get the high strain rate. But the moment you have the quasi-static strain rate, that means you are going for the low strain rate. Then only we'll find that one. Okay, and also that depends on, for example, this graph is going up to maybe this much of stress. Maybe, this depends upon material. Maybe some material it will go to here, and maybe some material it will go to here. That depends upon the material behavior, right? Is it fine? Okay. So, yeah, am I audible, right?
Yes, sir.
Okay, fine. So then how to find out, because whenever you are talking about the stress, strain, then also we are talking about here strain rate. So, very small equation we have. The strain rate is forming is directly related to the speed of the deformation, because what I told in the previous slide, the first definition, that based or that depends upon the speed of the deformation. So I put here the strain rate epsilon equal to V by H. So where V equal to the velocity of the ramp, because what the velocity actually you are putting that, and H I will show maybe after one or two slides, because I could not put this picture actually here. So maybe after one or two slide again I will put with a schematic diagram. So H equal to the instantaneous height of workpiece. Maybe you can tell this is height, or maybe you can tell that how much area actually it is deforming. So maybe the small length also you can tell. Okay. So in most practical operations, evaluation of strain rate is complicated by the work part geometry, because if you will remember in the first class I told about some of the schematic diagram of rolling, forging, extrusion, then deep drawing, or maybe the shearing. So this depends upon the work part of the geometry, work part geometry. Then the variation in strain rate in different regions of the part, because that part also you have to think about in which zone, because it's a big area. You cannot tell that only this is a small area this is affecting, because it's a big material you have. And the strain rate can reach almost 1000 per second or more for some metal forming operation. So if you have to think, because there is not only rolling operation, you have several deforming operations are there. Okay, or the metal working operations are there. So in case of, for example, rolling, so this mechanism will be different. In case of forging, that mechanism will be different, because you are applying the different load there. Okay, and the different system there. Yeah. So how the effect of strain rate on the flow stress you are getting, or what kind of parameters actually you are thinking. So the flow stress is a function of temperature. So whenever we are talking about, that's why in the beginning we talked about the metal forming, how you are dividing or how you are distinguishing with respect to the temperature. So at a hot working temperatures, flow stress also depends on the strain rate. Okay, whatever the equations actually we have studied, maybe in the previous slide only one equation. So maybe now also we have to talk about how you are relating the flow stress and the strain rate, how it is connecting to each other. You cannot tell that only the flow stress is one and the strain rate is one. So you have to combine somewhere. You have to make a link somewhere. And this effect is known as the strain rate sensitivity. So whatever the definition I put in the previous slide, so you can see the equation here. So the strain rate sensitivity equation, YF equal to C epsilon to the power M. So where YF equal to flow stress, I think yesterday I have discussed about the flow stress equation, YF equal to K epsilon to the power N, if you remember that previous class I have discussed. And C equal to the strength constant. Okay, so wherever we have talked about in the last class also, where YF equal to K epsilon to the power N, where K equal to the strength coefficient, right? So here also we mentioned this is the strength coefficient or strength constant. This is similar but not equal to the strength coefficient, because every time the terminology is same, but whenever you are measuring this value, actually the number, so you cannot tell that this is exactly same. Maybe it's somewhere it will be exactly same, but in other cases maybe it cannot be same. So where M equal to the strain rate sensitivity exponent. But in our case, what we have done when we mentioned the YF equal to K epsilon to the power N, N was the strain hardening. Okay, so here we are, when converting to the strain rate sensitivity, so M equal to the strain rate sensitivity exponent. right? Is it clear? So you can write it down. Maybe somewhere we will make some few small numericals. Okay, the equation just you can write. The PPT I will share later. So just you can write the equation somewhere. Okay. Yeah. So the same thing what I told, I will show the one schematic diagram. So how this trend rate actually, it will affect when you are going towards the elevated temperature. So that means when your chemical reaction or something is happening, so that we are conducting or that we are considering as elevated temperature. So if you will see the schematic diagram here, okay, so that means whenever you are giving some force here, okay, and in which velocity actually it is moving. For example, here, let's say v velocity is moving and you have the die here, and this much of distance, what I told in the beginning, you have the edge. Okay, so the edge sometimes we are telling this is height actually, but you can also consider as a length also, because how much of area or how much of a distance actually it is deforming there. Okay, so if you are deforming up to here also, you can consider from here to here, this is edge. Okay, but we are considering here as edge. For example, I put here, so this epsilon equal to v by h, whatever I put in the previous slides, and yf equal to c epsilon to the power m, and yf equal to c epsilon to the power m. These are all the equations I put in the previous slides. And where epsilon equal to the strain rate and v equal to the speed of the deformation could be equal to the velocity of the ram, and h equal to the instantaneous height of the workpiece. Okay, so do not be confused, because normally we are considering height is here from here to here, but you can also consider as this is length. This is not an issue, but at least you have to see that, or you have to, your fundamentals should be clear that this much of length or the height, this is deforming. That's why that much of height or the length we are considering. Okay, is it fine?
Yes.
Yes.
Okay. Yeah. So one more, when this slide just only I am showing here, maybe when you will do, maybe I do not know in future if somebody is interested about the research part. So I just put one slide here. So how we do not have any option if we have some material, maybe when you have the free time, maybe, or when you will come to the campus, maybe you can do in our laboratory, for example. So you can see here, this is the flow stress in the y-axis, and this is the strain. So effect of strain rate on the flow stress at an elevated work temperature. Okay, so how depending upon your material, you can find this kind of a graph. And similarly, if you have the same relationship, whatever the relationship you are getting, but if you are converting, or if you are plotting another graph with the log coordinates, so you can find this straight line. But how you will measure this one? So you have to make perpendicular lines, then only you have to measure this one. But here one more interesting thing, that if you are changing the temperature, let's say in the room temperature, you are getting this kind of lines. But if you are increasing the temperature 400, 800, 1200, or maybe you can add 200, 300, 500, 700. But if you will vary with various different temperature, so you will find proper graph. Because if you have only 2 or 3 temperature, just only you are varying, so you cannot find a proper graph, or you cannot make a correlation. This I am talking about research perspective. Okay, but otherwise, at least you will understand, because this one, when I am putting in the text, at least you will understand that when you are varying the temperature from the room temperature to the elevated temperature, or room temperature to the higher temperature, how actually this is changing. So here you can see, if the C, what we are actually, what is the basic meaning of this graph, this third graph, is if flow stress equal to the C. If flow stress equal to the C, then how much will be the strain? So the effect of temperature on the flow stress for a typical metal. So that means the constant C. So that means if the flow stress in the y-axis, if you are considering as equal to, or if you are telling that, or if you are considering that this flow stress is equal to C, so that means this point. So then how will be the strain rate? So that means if you can make a horizontal line here and you can make it fall, so that means you will find here 1. Okay, so that means the vertical dash line at a strain rate equal to 1 decreases, and m, slope of the each point, increases with increasing the temperature. Okay, so for example, if you have a straight line, then just how, with the help of that horizontal or maybe the vertical line, how you are calculating. If you do not have any data, for example, if somebody is asking if flow stress is equal to, let's say, C value, then how much will be the strain rate? Okay, so you can just make a line. If you do not have any data, if somebody is giving a graph, then only you will define that one. Fine. Yeah.
Yes.
Okay. Then next one, I think these are the in many cases. For example, if you will remember, in machining also we have talked about the friction. Okay, so whenever I gave maybe a lot of example in machining, whenever you are going by a motorbike or maybe car, how you are getting the friction. Similarly here also, whenever you are processing something, because you will find some resistance there, or you will find some friction behavior there, or the property there. So in most of the metal forming process, friction is undesirable. Okay, so what are the parameters, or what are the the properties you are getting here? So one is forces and power are increased. Okay, so if you have some forces there, or if you have some friction there, so what you will do, you have to apply some power, or you have to apply some force there to overcome that one. Then the wires are tooling faster. Okay, and the next third one is metal flow is retarded. Okay, so that means if you are getting some friction, some of the the property it will be affect. So what you will do, you have to do something. For example, yesterday somebody was asking that how to make the the remove the stress, let's say. So if you have some problem, you have to find some alternative. You cannot tell that no, this is only the process I have done, then I stop my work. No, you have to do, because why you are doing any kind of metal preparation? Because you have some customer, then the customer they are telling that I need this much of size. You cannot tell that no, this is based on our company, the system only we will prepare this one. No, according to the customer demand you have to do, whether he is asking about the billet, whether he is asking about the stress free. And sometimes also, if you will remember, or maybe somebody shared with you, sometimes in company you have waste product. So that waste product also some subsidiary company they are buying from them. Why they will buy? Because it will be they will sell in a cheaper price. So they will take that one and they will maybe recycle again, or maybe they will use some other purpose. So I gave some the typical result for this friction actually. So the friction and the tool wear are more severe in hot working. Okay, so if you will see the categories cold working, these are the almost in the similar zone actually they have already done. Like universal truth you can say. The cold working, you will find the temperature range already we have discussed, and the strain rate equal to 0 less than m and less than 0.05, and the coefficient of friction you will find 0.1. Similarly, if you will find warm working, the coefficient of friction is 0.2, and the hot working you will find 0.4 to 0.5. Okay, so these are the some of the variation when we are doing the cold working and the warm working and the hot working. You will find almost similar, or maybe very close to that. Okay, because you cannot see that, or you cannot tell that the theoretical result and the experimental result, it will be totally different. And whenever we are making a laboratory scale, sometimes it will be much more accurate, because in laboratory we are taking very small sample. But whenever you are going for the big industry or the bigger scale, then somewhere it will be vary, because you are going for the mass production, and the samples or the the raw material will be much more higher. Okay, so that's why whenever we are going for, maybe yesterday we are talking about that how the demand actually. So that also to make some industrialization. So you have to go initially for the laboratory scale. So you have to get the success, then you have to go for the pilot scale. So that means you have to increase. Let's say you are taking 5 gram or maybe 10 gram in the laboratory. So you have to go for 30 kg or maybe 50 kg or maybe 100 kg. Okay, so if the pilot scale again success or maybe not success, then again you have to go back to the laboratory scale. If it is totally success, then you have to go for the main industrialization or bigger scale. Okay, so this is the normal process. Yeah. So one more thing, you have the lubrication in metal forming. When you are doing some metal forming in machining, also we have talked about the lubrication. A lot of lubricating materials or lubricating the ingredients we have discussed. So here also the metalworking lubricants are applied to tool work interface in many forming operation to reduce harmful effects of friction. So it is connected. It is connected to the resistance, or it is connected to the friction. Okay, so you have to use some lubricants. So first is reduced sticking forces and power tool wear. Okay, so while you are using lubricant, this is almost we know, because in machining we have covered what is the basic meaning of or use of the lubricant. Then you will get the better surface finish, and also removes heat from the tooling. Okay, so whenever sometimes the last time I think Charles, I remember he was trying by himself. So he bought some cutter, then he was trying to understand that why this is important. Maybe in some other purpose, in in other way we were doing. But similarly, at least we have to understand that what is the basic meaning of the lubricant whenever you are doing any kind of metal forming or maybe machining operation. So whenever you are choosing one lubricant, so what are the basic parameters you are thinking? So one is the type of forming process. Okay, what kind of forming process you are doing, or maybe you are using, for example, rolling, forging, or extrusion. Then also the hot working or cold working, whatever the depending on the temperature of what we have discussed yesterday, and then the work material. So now you can understand. You cannot make a generalized thing. Maybe sometimes what I told about the friction coefficient, maybe these are almost similar. So that's why they have established something. But whenever you are choosing some lubricant, that depends upon the material, the technology, the process, the temperature, what kind of temperature you are using, then ease of application, and then cost also. Then, for example, the cold working, hot working, normally we are using several times the mineral oil, or maybe somewhere we are using some coatings, or maybe some soaps also sometimes we are giving. So this is basically when we are talking about the lubricants or lubrication in metal forming, right? Is it clear?
Yes, sir.
Yes, sir.
Okay, so now I have put maybe small numericals for you. So just you can, I just open small because in the bottom I have the answer. So just you can read the question and then do by yourself. A metal has a flow curve. Okay, a metal has a flow curve with parameters k equal to 850 megapascal and strain hardening exponent n equal to 0.3. A tensile specimen of the metal with gauge length equal to 100 millimeter is stretched to a length of 157 mm. Determine the flow stress at the new length and the average flow stress that is the metal has been subjected to during the deformation. So that means you have to all the you have to find out what are the maybe old students, you have all aware of the process how we are writing, but for the new students just I will emphasize that whenever you are doing any kind of numerical, maybe because this numerical I have just mentioned k equal to this one and n equal to this one, but in the exam I will not write k equal to this much and n equal to this much. I will write the the phrases of k. Okay, so that in exam what you will do, you have to write the given. Okay, so given, do not write k equal to this one. Okay, so you have to write that the strength coefficient equal to k equal to 850 megapascal. Okay, so that means this is given. Then what you have to find out, determine the flow stress. Okay, so flow stress equal to question mark, right? Then you have to go for the answer. But if you are writing very clearly, because otherwise how I will know? Of course I know, you also know what is k, but in the exam you have to write everything in detail, so that for the any kind of evaluation somebody is doing, it will be much more clear that the student has known the process. But some students, they are worried about the answer. Do not worry about the answer. If answer is wrong, maybe it is coming minus or plus, you do not need to worry, but you have to go step by step the process. Okay, so that is the basic meaning, because otherwise if only you are calculating, because it's open book exam, so all the equation you know, all the arithmetic we know, so that there is no meaning to give the example or the numerical. Okay, is it clear?
Yes, sir.
Okay, so please do by yourself, maybe 2 minutes you can just take, then I will show the answer.
Sir, 718 megapascals.
718 megapascal.
Yes.
1 second. No, I think. Have you calculated epsilon? How much?
0.57.
0.5. Yeah. And then flow stress 700, na?
Yes, sir. 718.
Maybe. Okay. And the equation what you put? YF equal to?
YF equal to K into epsilon power n. Sir.
Yeah. Okay. And determine the flow stress. And what is the average flow stress? Because this is two questions. Determine the flow stress at the new length and the average flow stress. Two things it is asking.
I haven't done that. Sir.
Yeah. Other students, please try to find out if you write the given what are the value is given, then it is very much you will understand that which equation, because only 3 equations we have studied, so you will get to know that which equation I will fit there, very small equation. Okay, then you have to, and unit is much more important. Another thing I forgot to tell you, that whenever you are writing, many students, they are missing the unit, because unit is important. We are not asking maybe whether 700 or maybe 800, we do not need to worry. We need the process you are getting or you are doing, then the unit, that is much more important. Other student, what about Amal? Is it fine? You are getting?
Yes, sir. Trying.
Okay. whenever I'm teaching you, the equation you can write immediately in the notebook, because otherwise we have to go back the equation, then again you will see. So equations at least, text you do not need to write because I will share. Equation just you can write, because whenever we are doing some numerical, it will be better to find out the equation immediately, because you cannot remember everything immediately. Okay. Charles, epsilon, what was the equation?
Like change in length by original length.
Only change in length by original length. Or ln change in length by original length. Because you are integrating from 0 to epsilon, 0 to L, sorry, L to L0, right? So it will be ln change in length by original length. So ln 157 by 100. Done.
Sir, could you show how to calculate the average flow stress?
The equation.
Yes, sir.
One second. Where is that equation? Yeah. Yeah,
Okay,
this
sir.
one.
Yes, sir.
Yf equal to k epsilon to the power n divided by 1 plus n.
Okay, sir.
Yeah. So can you see the, because you have to write the given, okay, so that one I have not write. So the given you have to write k equal to 850 megapascal, n equal to this much. So if you want to find out the epsilon, ln, the change in length, that means the length you have made it. So 157 by 100, so you'll find 0.5. Okay. So the flow stress, the equation is YF equal to K epsilon to the power N. Okay, so you will get around 670, maybe I do not know the answer, probably you can check. I think Charles is getting 718 probably. Okay, you can cross check this one. Then the average flow stress, the K epsilon to the power N divided by 1 plus N. So we'll get around 515 megapascal. Okay.
Yes, sir.
Yes, sir.
Okay. So is it clear?
Yes, sir.
The average flow stress answer is right, Charles?
Yes, sir. I made a mistake.
Okay, fine. Other students, are you getting the small equation only? Maybe in when we will go for the rolling forging, I think you will find big equation. So make a small practice now, a small equation, then we'll go for the bigger one when we'll go detail in module 3 and 4. Okay. Is it clear from other student?
Yes, sir.
Yeah.
Yes,
Okay,
sir.
fine. So then one more example, just you can write here for a certain metal. Can you see the example too? I'm just taking smaller, otherwise the answer is there. Okay. So for a certain metal, the strength coefficient equal to 700 megapascal and strain hardening exponent equal to 0.27. Determine the mean flow stress that the metal experiences if it is subjected to a stress that is equal to its strength coefficient K. Okay, so please read the question twice. So maybe then you have to find like what is the given, then what to be find out. If you need any equation, please tell me so that I will go back to the slides. So you have to find out the mean flow stress. What is the equation of mean flow stress?
Sir, it's the same as average flow stress, right, sir?
Yeah, Amar, yeah, fine. You know, this mean flow stress and the average flow stress both are same. Okay. And the equation you can write K epsilon to the power N divided by 1 plus N. This equation will help you to find out the mean flow stress. Other students, please participate. Only Charles and Amal both are only participating.
So what is the n value in this case?
It is given, na? Just you can read the question. N is given, I think. Strain hardening exponent, na?
Oh, okay.
Okay. 0.27. So, better what I'm suggesting, because now the examples are very small, but whenever you will go for the bigger numerical, you have to read the question twice or thrice. Okay, so then write the given. Do not go directly that this equation and I will put the values and I will get the answer. Okay, do not do. You have to go step by step given, then you will better understand. Okay, because now this is very small, only one equation you are applying, or maybe two small equations. Okay. So what is the value of epsilon here? Anyone? Are you You need epsilon value here? No, all become silent.
Sir, on the equation it says we need.
So what should be the value? Any idea, guess? No? Any data is here, epsilon data?
So the x-axis it's given, no, sir.
Yeah, no, I mean now, yeah, this is epsilon, na? This one. Okay, so now what should be the value here? What is the question it is written? In the question it is written, determine the mean flow stress that the metal experiences if it is subjected to a stress that is equal to its strength coefficient, Okay, so if it is equal to the strength coefficient, though how much will be the strain rate? What will be the strain? EE, 1.
Yes, sir.
Right? So you can use 1. So that's why I repeated here also when I was explaining, I was repeatedly, I told in another way that if the flow stress equal to the strength coefficient, then what will be the epsilon? Okay. So now you can use 1, this one. Okay. So if YF equal to K equal to the 700, it is given 700 into epsilon to the power 0.27. Okay. So epsilon you are considering as 1. So YF bar equal to this much value. 551. You can just cross check.
Yes, sir.
Okay. So, small things, a little like, you need a little tricky. Okay. So you have to read the question because everything is there in the question. If not there, then you can tell, sir, there is nothing. But if you will read the question twice or thrice, you will understand all the value. And if you will write the given, again, I'm repeating, if you write the given, then based on that given, you have to put the equation. Because let's say now after 2 module, then you will find, let's say 10 equation. So which one you will fit somewhere, right? So one more, the final, one more example, just you can write, small one. Determine the others, have you done?
So this current which you're doing, why did we not take log?
Which one?
Ln of the values you have not taken. That's because it's not disturbed, I think so.
I will explain which one.
So the question number 2.
Yeah. So, if you have the value of YF equal to K, because this is given, determine the mean flow stress that the metal experiences if it is subjected to a stress that is equal to its strength. That means the YF equal to K is given. And this is the equation, YF equal to K equal to K, or YF equal to K epsilon to the power N. Okay. So if YF equal to K, so that means this equation equal to 700 epsilon to the power 0.27. And here only what you need to value, the epsilon you have to need. So epsilon equal to 1. Okay. So that means this value you will get, YF equal to, you already know. So then only YF bar, the equation equal to K epsilon to the power N divided by 1 plus N. So you will get this value. Right? Am I clear?
Okay, sir.
Okay. And the third numerical, determine the value of the strain hardening exponent for a metal that will cause the average flow stress to be 3/4 of the final flow stress after the deformation. Okay. So what you will find out? Determine the value of the strain hardening exponent. What is the strain hardening exponent? N, right? Yeah.
Yes, sir.
Yeah. So
Yes, sir.
yeah, just you can maybe 2-3 minutes you can finish it. Just you can try.
Maybe we have to equate the average one with the final one
Yeah.
with 3
Yeah.
by
Yeah. Yeah. So
solve
that means
N.
YF bar equal to 3/4 YF. Yeah.
1/3, sir.
So then instead of Y bar F, you can put the equation. Okay. Whatever you have used that equation several times, then you can equate with 3/4 YF. So you will find out N.
Is N 1/3, sir?
1/3.
Yes,
Yeah.
sir.
Yeah. 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 But you can make it a point, na? Don't put 1/3.
Okay.
Put it 0 point something. Other students are, when very silent, only 3-4 only students are now. But you have to participate because small equation now we have to go for the bigger one. So at that time you will be confused again. Okay, so we will do some good numerical, because otherwise how we will know the application? Only to study the equation only. Okay. You can see here. 0.3, right? The answer.
Yes, sir.
Okay. Just you can cross check whatever the systematically you have to write. I have not mentioned here. Given you have to write. Okay, given, but do not write only the term k. Okay, so you have to write the strength coefficient equal to k equal to this one. Okay, x, and also you have to write the unit. If no unit, then you don't need to write. Fine.
Yes, sir.
Okay. Okay. If any question, you can ask. Otherwise, you can stop.